Hey, it's Matt. In this video, we are going to learn how to detect light using a light sensor and an Arduino. Once you've got this knowledge, you're going to be able to build cool projects such as this Halloween prop whose eyes glow, but only in the dark. Today, we're going to look at two sensors that allow us to detect light with the Arduino. The good old-fashioned light-dependent resistor, or LDR for short, and the often superior option, a phototransistor. Both are available as just a bare sensor, which can be integrated into your own circuit board, as well as breakout boards that make them even easier to use. I'll show you how to hook up both types of sensors using both the bare and breakout board versions. An LDR, or light-dependent resistor, is one of the simplest and most commonly used light sensors. You've probably seen it in other tutorials, and if you've ever bought one of those Arduino sensor kits, you almost certainly have one. It's a passive component that changes its resistance based on the amount of light falling on it. When light hits the surface of the LDR, its resistance decreases, allowing more current to flow through the circuit. Conversely, in the dark or low light conditions, the LDR's resistance increases, reducing the current flow. This sounds perfect, but there are some disadvantages. First off, did you know that LDRs are banned in the European Union? That's because their ability to respond to a wide range of light comes from using cadmium sulfide. It's a pretty toxic heavy metal that you don't really want in or on your body. It's still fine for use in hobbyist projects as long as you're not breaking them apart and playing with the cadmium itself, just like sensors that contain mercury. LDRs also tend to be relatively slow in reacting to changes in light, especially when going from bright light to darkness. Although you still see LDRs being used a lot in hobby projects, in most cases I strongly recommend using a phototransistor instead. Aside from not containing cadmium, phototransistors have some other great advantages. They can respond to changes in light as much as 1,000 times faster than an LDR, and they can also be sensitive to much more specific wavelengths of light. For example, you can buy phototransistors to specifically measure changes in infrared light. Phototransistors take advantage of a photoelectric effect just like LDRs do. When photons, or light in other words, hit the phototransistor, it allows current to flow from its collector to its emitter. I have two examples of phototransistors in front of me. First, I have an Adafruit 2748 breakout board. This board uses the ALS PT19 phototransistor, which has a peak wavelength of 630 nanometers. It also has a resistor already included on the board, which makes it easier to use with your Arduino, as we'll see in a second. I also do have just a bare through-hole phototransistor with me. This is almost as easy to use as a breakout board, and it gives you a lot more flexibility when building your project. This particular phototransistor is the TEPT 4400 from Vishay, which is sensitive to a pretty broad range of visible light, but peaks in the 570 nanometer wavelength, which falls right between green and yellow. We're going to build two versions of this circuit, one using breakout boards and one using the bare sensors. You can get schematics for both in the video description, along with a list of all of the components that we used. Here's what you're going to need for this demo. First and foremost, you're going to need one of these sensors that we talked about on a breakout board. So again, I'm partial to a phototransistor. Doesn't have to be this exact breakout board, but it is what I would recommend. If you do choose to use an LDR like this one, that's fine too. The circuit will actually work identically. Next, you're going to need some type of Arduino. I personally prefer the Nano. I have a bunch of Nano clones that I use for all my projects and they work great. But if you have an Uno, you have a Mega, you have something else, you have one of the newer Arduinos, that should all be fine as well. We're going to have some fun with this demo. We're going to control the brightness of an LED using one of these sensors. So we are, of course, going to need an LED along with a 220 ohm resistor for the LED itself. It can be a little bit of a bigger or smaller resistor value as well, and that's fine, but something in that general 220 range. And then last but not least, we are going to need a breadboard, some wire, and some sort of 5-volt power source in order to power our project. If you plan to proceed with the second part of a demo, there are a couple more parts you're going to need. First, you will need at least one bare light sensor. It could be a phototransistor. Again, this is the TEPT 4400, or an LDR, or if you want, get both and experiment with the differences. You're also going to need some resistors, and to properly appreciate the demo, I suggest several resistors like I have here. I've got a 10K, a 68K, and a 270K. You do not need these exact values, just get something in that general range. Let's build our circuit. To make things easier to follow, I'm going to start with the connections on the Arduino, and then we'll switch over to the breadboard. I'm going to start with our analog input pin that's going to read from the sensor. I'm going to use A0. You can use any pin you want as long as it's one of the analog ones. Next, I'm going to attach a wire to D9. That is going to control our LED, and that needs to be a pin that supports PWM, which D9 on the Nano does. Now let's get our power hookups taken care of. We always want to make sure we connect to ground, and you'll see how that works on the breadboard. And because we do want to be able to power the rest of the circuit and possibly the Arduino itself, we are also going to have a hookup to the 5-volt pin like so. Now we can get our circuit built on the breadboard, starting with the light sensor itself. We can put that anywhere on the breadboard. Just make sure that the light sensor is facing up and not covered by the breadboard. And your sensor is going to have 3 pins. So let's wire these up one by one, and be careful because they might be in a different order for you. First thing we want to do is hook up power. So that's probably going to be labeled with a plus sign. So I'm going to go ahead and hook that up to the positive power rail. Next, we've got the pin that the Arduino is able to read the value from. On mine, it's labeled out. It might also be labeled S. And that's where we want that A0 pin on the Arduino to be connected to. And lastly, to complete the light sensor circuit, we want to hook up ground, which is going to be labeled as GND, or possibly just a negative sign, to the ground on the breadboard. Next, we've got the LED. Polarity is important on LEDs. The longer lead is the anode, or positive lead, and then the shorter one is the cathode. We're going to hook up the cathode to ground. Then we'll connect the anode to that 220 ohm resistor. Finally, we hook up the D9 pin of the Arduino to the other leg of the resistor. That's going to allow the Arduino to light up the LED. Last but not least are the power connections from the Arduino. So I'm going to hook up the ground pin to the negative or ground rail on the breadboard, and that 5-volt pin to the positive rail. And again, yours might be 3.3 on the newer Arduino. In this configuration, we can actually power this whole circuit off the Arduino, and then we can power the Arduino itself from either the USB on our computer or simply from a normal 5-volt USB charger. Alternatively, it's also possible to hook up an external power supply, just making sure it's either 5-volt or 3.3 volt, depending on your Arduino, to the positive and negative power, and that would actually allow the Arduino to be powered without being hooked up at all through its USB. Now that we've got things hooked up, we'll need some code to make it work. Ta-da! This code does the following. First, we define each pin that we want to use. Photo pin is the pin for reading the phototransistor. Make sure this matches the pin that you connect the transistor to, and be sure that you are using an analog pin. That's important for detecting the change in brightness. If you use a normal digital pin, you're just going to be able to tell if it's very bright or not bright at all, and nothing in between. Likewise, we also define the pin that we hooked up the LED to. In this demo, we hooked it up to pin 9. It is important to hook it up to a pin that supports PWM so that we are able to change the brightness of that LED. Now, in the setup function, we're accomplishing 2 things. First, we initialize serial communication. That's going to allow us to write to that serial output window when the program is hooked up to our computer. And we're also going to set up the LED pin in order to be an output pin. And that's what's going to allow the Arduino to power that pin and therefore to actually change the brightness. We don't need to do anything with the photo pin because that's going to be set to input by default, and so that's why you don't see it mentioned in the setup function. Now we get to the loop function. That's the code that's going to execute over and over. First, we're going to read the value from the sensor pin. That's going to come to us as a number between 0 and 1023, with 0 representing no light hitting the sensor at all, and 1023 representing the sensor being fully saturated. In the next line, we're going to output that value to the serial port, so that way when the Arduino is connected to our computer, we can see in real time the actual value that we're reading from the sensor. That's going to be very useful for any sort of troubleshooting. Now that we have the sensor value, we need to decide what we want to do with this information. In this example, I want to make the LED glow brighter when it's dark in the room, and to lower the brightness when the room is bright. This map function handles that for us. We're taking that value that's going to be between 0 and 1023, and we're going to convert it to our brightness level for the LED. In the Arduino system, the PWM output pins take a value between 0 and 255, so that's where we're mapping things to. And because we want the LED to be bright when the room is dark, we've actually reversed the order of those values so that 0 is going to map to 255 and 1023 is going to map to 0 on the LED output. Now, if I want, I can put a small delay statement here to make the LED brightness a little more stable. Go ahead, get that code into the Arduino IDE. I do have that code file in the video description. Get it uploaded to your Arduino, and then let's go ahead and test it out. Okay, this is attempt number 1. I have everything hooked up. Let's see if this actually works. I'm going to put my finger over the light sensor. And yep, sure enough, the LED did get brighter. And on the screen, I do have the output from the serial monitor, so we can see the value that we're getting from the sensor. Let's just try that again. You can see the sensor goes down to pretty much close to 0. We even do get some zeros coming out of a monitor. And when we just have the ambient light in my shop, we do have values that are closer to like 300-400. Okay, so let's see if we can make this demo a little bit more visible by responding to the light sensor a little bit more intelligently. So really, I want to do 2 things. First of all, I want that LED to go dark when the light is on in my shop, so that we can really see that we're responding to that light sensor. And I also want slightly more reliable values for the sensor itself because, again, we're getting such big ranges. So we're going to tackle problem number 1 first. Right now, I am reading the sensor value once. So let's see if we can get a better value by reading the sensor more than once. What I'm going to do is I'm going to make what's known as a for loop. So this is basically just reading the sensor value 3 times and then taking the average of those 3 measurements. And what that should do is that should give us a much more stable reading. So I am going to test this and let's actually see what that looks like. Okay, so you can actually see we do have values primarily between 200-ish to 400-ish. So I'm going to do something a little bit different here. Instead of just changing the brightness of the LED according to the light level of the room, let's actually turn the LED on and off based on whether the lights are in the room. So this is a great example of being able to use the sensor to decide whether to activate something or not. So in this case, if the light value is greater than 50, so we've kind of saw that if it's over 50, then the room is probably pretty lit up. Actually, let's make that 100 to be safe. So if it's over 100, we are actually going to set the LED brightness to 0. Else, we're going to light the LED up completely. So now we're simply turning that LED on and off instead of worrying about changing the brightness to like half brightness, quarter brightness, etc. And let's see what sort of impact that has. Oh, and I made a coding error, so we need to declare our variables first. Okay, so notice that the LED is now off. The code's been uploaded, but the LED is not shining. That's exactly what we want. And as soon as I put my finger over the sensor, sure enough, the LED lights up. Let's check it out by actually turning off the lights. Boom, check that out. That is so cool. And you can see, thanks to the phototransistor, the LED responds basically immediately. As far as we're concerned, for something like room lighting, this is instant. If you've made it this far in the video, you now have everything that you need in order to detect light in your Arduino project and build something really cool. In fact, I'd love for you to comment down below and let me know how you've been using this information in your own projects. But we're not done yet. Let's push our knowledge one step further and learn how to use a bare sensor like this phototransistor in order to accomplish the same thing we've already done, but with some more flexibility and the ability to use any sensor that we want. We're going to begin with the circuit that we already built because most of it's actually going to stay the same. What's going to be different is instead of using a breakout board, which integrates a sensor and a resistor, we are going to build that circuit ourselves as part of what we've just created. So I'm going to remove the sensor here. And instead, I have just a phototransistor all on its own. And you'll notice that the phototransistor has two legs, and one is longer and one is shorter. The shorter one is the emitter, the longer one is the collector. What we want to do is we want to hook it up so that the collector is connected to our 5-volt power. And by the way, this particular sensor can go as low as 2.5 volts. So if you're working with a 3.3 volt Arduino, that's fine. And then we want the emitter to be connected to where we had our analog pin connected on the Arduino. So that basically means it's just going to slot right in here. There we go. So now what we need is a resistor because again, you'll recall this breakout board has the sensor and it's got a resistor. So that means we must need a resistor in our new circuit. I'm going to start with a 10K resistor and then I'm going to use the other ones to show you something really cool. So I want this resistor also connected to the emitter pin of the phototransistor. So that's going to be connected in the same spot that we've got the Arduino A0 analog pin and the phototransistor emitter. And then the other leg of the resistor we just need connected to ground. And we happen to have a ground connection here. So that's where this resistor is going to go. Okay, so that's the resistor connected to the emitter pin as well as to ground. I did move my ground connection slightly just to avoid squishing the resistor, but it's the exact connection that we just described. And that's actually everything that we need to do because we've just replicated the functionality of the breakout board all by ourselves. But one cool thing is now we're not committed to having this phototransistor right on our circuit board. We could have wires going to this phototransistor, and this phototransistor could be in a completely different spot in our project in places where maybe a breakout board won't fit. Now, let's see if this even works. Okay, we've got power hooked up. Let's see what happens when I put my finger over the phototransistor. Oh, look at that. It does still work. We have done the exact same thing as that breakout board. Isn't that cool? But that's not actually the whole story. Let's head over to the serial monitor and let's see what values we're receiving from the phototransistor. Okay, so we can see that the numbers that we're getting from this sensor are a little bit different than the last one. These are all in the hundreds. And then if I put my finger over the phototransistor, I'm only getting about 80, 90. And I'm actually going to turn off the lights in the room and see what happens then. So even in a pitch dark room, the sensor is still reporting 70. So as you can see, with the current setup, we actually have a much more narrow band of numbers than we did before. Pitch dark basically seems to be about 70, and a pretty brightly lit room set up for filming is only about 180. So that doesn't actually give us much range to work with, and that's probably going to give us a pretty buggy program that's not always going to behave the way we expect. So let's fix that. The trick here is all in the resistor value. I chose a 10K resistor, which with some sensors will actually work just fine, but to get the proper range for your particular environment and your particular sensor, you do actually want to experiment with resistor values. The higher the resistor value, the more sensitive it's going to be to changes in light coming into the sensor. So instead of this 10K resistor, let's try putting in the 68K one and see what happens. Okay, interesting. So I put in that 68K resistor, and right away on the serial monitor, we see values that were much more similar to the previous sensor that we were using. I still have nice, bright indoor conditions, proper for filming, and I'm getting values in that 300 to 400 range that I was before. And now when I put my finger over the sensor, I'm getting values in about 100, 120. So let's see what happens if I turn off the lights. So we can see that in pretty much pitch dark, we're getting about 90 as lights are off. And that's fine. That gives us a pretty big range to play with. So it's very easy to set this program correctly. So it's going to turn the LED on and off when we expect. But let's now try this 270K resistor and let's see what kind of behavior we get there. And take a look at that. Now in a pretty brightly lit room, we are actually getting values in the 800 and 900 range. So that means the sensor is now reporting that as being quite bright. And now if I turn off the light, I am getting values in about the 100 range. And that's probably pretty good because there is actually still light coming into the sensor from my laptop screen. Now I've turned my overhead lights on, but I've left my filming lights off. And check this out. Now we're in the 300 to 400 range. And now we're quite bright again. So notice what we've actually done here. By experimenting with resistor values, we found one that gives us a broader range of values to work with when we're reading from the phototransistor. That means we can have our project behave more consistently because it's easier to identify a threshold where things are dark. In this case, I'd probably set about 150 or lower to be the value at which the LED turns on. And then anything above that, I can leave the LED off, or I can start gradually increasing the brightness of that LED. Now you should be able to use light sensors in your own Arduino projects. Once again, be sure to comment down below and let me know what it is that you've built yourself. And of course, make sure to like and subscribe this video so that you see more tutorials as they come out.